Hello, good morning everyone. I am Narsimurthy, presently working in a government first grade women's college Tumkur. I am going to present a video of subject physics. This is the 29th video. I mean to say it is the 29th session for the second semester BSc students of Tumkur University. Here one complete unit is over. So we have 4 units, so 1 unit is over. In the second unit I am presenting the 29th video. I mean to say it's a 14th video in the second unit, last but one video. So in this small chapter of 5 hours chapter, which is the electromagnetic induction, I discussed about a very famous 3 laws of electrostatics. So one is the Faraday's first law and the Faraday's second law. Another one is the Lenz law. These are the 3 important laws when we come across the electromagnetic induction chapter. These 3 laws you have studied in the second PUC as well. The first Faraday's law says that it states that if there is a change in the magnetic flux linked with the coil, an EMF is induced in the coil. Okay, so this is what the Faraday's first law is. An EMF is induced in the coil when there is a change in the magnetic flux linked with the coil. So current keep on inducing as long as there is a change in the magnetic flux. Once the change in the magnetic flux stops, the induced current will also stops. The second Faraday's law says that the EMF which is induced in the coil is equal to the rate of change of magnetic flux. E is equal to d phi by dt. That's what the Faraday's second law. And the Lenz law will gives us the direction of the induced current. The current is induced in that direction that it opposes the cause for the production. The current which is induced will opposes the change in the magnetic flux. These are all the 3 very important laws of electromagnetic induction. After that we have discussed a derivation. So one is the self-inductance derivation. We have derived an equation for self-inductance of a coil L. After that we derived an equation for mutual inductance M, and then I derived an equation for energy stored in the coil. Okay, these are the 3 important derivations we come across here in the electromagnetic induction chapter. Now here in this last session we see what is actually the eddy current is, how the eddy current is produced, and what and all the applications of eddy current which we see in our day-to-day life. Okay, so here the current induced in a thick metal sheet. Here it is not a coil, it is a thick metal sheet. The current which is induced in the thick metal sheet, again it is induced because of change in the magnetic flux linked with it. Yeah, what actually happening is the Faraday's first law. The magnetic flux linked with the metal changes, an EMF is induced and current is induced. Same thing was happening here, but only the difference is here it is not a coil, it is a thick metal sheet. Now the current is induced in a thick metal sheet because of change in magnetic flux linked with it. The current which is induced is called eddy current. This current is called eddy current. And these currents was discovered by Foucault, hence they are also called Foucault current. You can call it as eddy current, you can call it as Foucault current also. Okay, because this is the current which is induced in a metal sheet, not in the coil. Induced in a metal sheet due to the change in the magnetic flux linked with it. Okay, so this is what the eddy current is. Yeah, now this metal sheet is placed in a changing magnetic field, a change in the magnetic flux linked with it. Because of this change, a current is induced in a metal sheet in accordance with the Faraday's law, and this current is known as eddying. That's what I said. Okay, so magnetic field changes, flux will also change. Because of change in flux, current is induced in accordance with the Faraday's law, and this is called the eddy current. So this current flows in a circular path, and the direction is again governed by the Lenz's law. Lenz's law is which decides the direction of the current which is flowing in a circular path in a metal sheet. Whether it is clockwise or it is anti-clockwise, it is decided by the Lenz's law, according to the Lenz's law. So this is what the eddy current. Now we'll see an experiment now. I'm looking at an experiment and see what is happening actually with the eddy current. Now what is this experiment is, a flat copper plate is allowed to swing in a non-uniform magnetic field perpendicular to the plane of a plate. So magnetic field is perpendicular to this plate. Now this plate is swinging in a non-uniform magnetic field. Okay, we have a field, horizontal field, and this plate is swinging vertically in a non-uniform magnetic field, and the magnetic field is perpendicular to the plate which is swinging. Now what actually happens? Eddy current is induced when plate enter and leaves the field. Now this is the area of the magnetic field. When this plate enters the field, eddy current is induced. When it leaves the field, again the eddy current is induced. So this eddy current will retarding force which damps the oscillation. This eddy current will produce the retarding force which damps the oscillation. How actually the eddy current will produce a retarding force and how this oscillation is stopped? Okay, I'll explain you that. I will explain you how the oscillation ceases, how it is damped, how the retarding force is produced because of the eddy current. Now at equilibrium position, this is one extreme position, this is another extreme position, the middle one is the equilibrium position. At equilibrium, flux through the plate is maximum. The magnetic lines of forces which are crashing the plate is maximum. Exactly at the midpoint, you can expect a maximum flux lines to pass through it. As it starts moving towards one extreme position, the plate is swinging. At equilibrium, maximum flux. When it moves to the extreme position, the area of the plate which is linked with the magnetic field decreases. Now the magnetic field is like this. So now the area is moving that way. So area linked with the magnetic field will decrease. Hence the flux will decrease. Hence the flux which is passing through this metal plate will decrease. This induces a large current. That is what we want for the eddy current. This is what we want for the induced current. We want flux to change. So flux is decreasing. It is enough. If it decreases, it is enough that current will increase. Current will be more. Induced current will be more. So what I want exactly is the change in the magnetic flux. Either it is decrease or it is increase. So in equilibrium, you can expect maximum flux. When it goes to extreme position, the flux will decrease. When flux will decrease, the current will increase. Okay, according to the Lenz's law, the induced current should oppose the motion of the plate, because the motion of the plate which was the responsible for the change in flux. The motion of the plate is what responsible for the induced current. So therefore, according to Lenz's law, this induced current in the metal plate should oppose this motion of the plate towards extreme position. It should not allow this plate to move towards extreme position. If it moves towards extreme position, flux decrease and the eddy current will increase. So eddy current should oppose the movement of this. Similarly, when the plate move towards the equilibrium position, flux increase again and the induced current will increase in the opposite direction. And motion of a plate is opposed. Now the motion of the plate is opposed in either case. Therefore, oscillation of the metal plate is damped. Okay. So eddy current produced in the metal plate, this eddy current opposes the cause for the production. It opposes the change in magnetic flux. It opposes the motion of the metal plate. Therefore the metal plate is damped. Okay, this is what actually happening. The free electrons in a metal disc or a metal plate whirl about within the plate as though they are caught in a eddy. Here is a metal plate which is swinging. Now we have a free charges which are moving in a metal plate. It is like that the free electrons are caught by the eddy current. Because of low resistance in a metal plate, because I am taking a copper metal plate, so it has very low resistance, therefore you can expect a very large induced current. If induced current, induced EMF is small, energy dissipated in the form of heat. The energy will be dissipated in the form of heat. Okay, if there it is small, here it is wasted as in the form of heat. Strength of eddy currents can be reduced by cutting the plates into number of thin sheets and are electrically insulated from one another. Now instead of taking a very thick metal sheet, what I am doing is I am cutting this into number of thin sheets and I am insulated one sheet with the other sheet. Okay, insulated from the other sheet by covering some insulating material between that. So by doing this, I can reduce the strength of eddy current. Right, we have many applications of eddy current in your syllabus. So 5-6 applications are mentioned in your syllabus. This is one of the important questions to be asked in the exam. So we'll go one by one. We'll go application of the eddy currents one by one. The first application is electromagnetic damping. Right. So you know what is damping is. Damping means the oscillation has to be stopped. You need to stop the oscillations for damping. Now what is actually the electromagnetic damping? When coil is wound on a metallic plate or a metallic frame instead of non-metallic frame, if some coil is wound on a metallic frame and oscillates in a magnetic field, if this coil oscillates in a magnetic field, definitely eddy current is induced in the plate, and this eddy current will opposes the motion of the coil and that bring the plate into the rest quickly. This is called electromagnetic damping. So oscillation of the plate is reduced by the eddy current which is produced in the plate because the plate is oscillated in a magnetic field. So this is called electromagnetic damping. Right. Second one is induction furnace. These induction furnace are used to produce very high temperature to separate the metal from their ores, metal extraction from the ore. Actually they take the ore, they heat it at a very high temperature by this induction furnace and they will extract the metal from the ore. And also sometimes they prepare alloys with this high temperature. Okay, this can be done with high temperature by using the induction furnace. How actually the temperature will be produced in the induction furnace, we will see. The principle behind this is the eddy current. A high frequency oscillating current is passed through the coil. High frequency alternating current. When an alternating current is passed through the coil and this is surrounded by the metal to be melted. So I have a coil here. The coil is surrounded by the metal to be melted. As a result of eddy current induced in the metal, produce sufficient high temperature to melt these metals. What exactly I am doing? I am passing the high frequency AC current to this coil. So it produces a varying magnetic field and we have a metal around it which has to be melted. In this metal an eddy current is produced. This eddy current will increase the temperature and this high temperature is sufficient enough to melt this metal which is surrounded by which surrounds the coil. And the coil is the thing where we are supplying an oscillating alternating current, high frequency alternating current. We'll move on to the third applications of eddy current. Third application is induction motor. Now, how actually the induction motor works? It's the basic principle is the eddy current. A metallic cylinder is placed in a rotating magnetic field. Now the metallic cylinder, a drum, is placed in a rotating magnetic field. So this is enough that eddy current is produced. Eddy current is induced in a magnetic cylinder. Now when this eddy current induced decreases the relative motion between cylinder and the magnetic field. This will decrease the relative motion between the cylinder and the magnetic field. How actually this decrease the relative motion between cylinder and magnetic field? It cannot touch the magnetic field. It cannot increase or decrease the magnetic field, because magnetic field is in my hand. I can increase or decrease, but these eddy currents, we cannot change my magnetic field. What eddy currents can do is, they can do with this drum, they can do the things with this metallic cylinder. They can rotate this metallic cylinder in an opposite direction. I am rotating the field in one direction. This eddy current will rotate this cylinder in the opposite direction. As the magnetic field is continuously rotated, the metallic cylinder is set into rotations because of the eddy current, due to this eddy current. Therefore, in this way, the induction motor will work. The fourth application of this eddy current is used in electric brakes. So we have seen in trains that this electric brake principle is used, and the idea behind is the eddy current. The braking effect of eddy current is used to stop the vehicle, such as electric trains. What actually happening here is, we have an axle of the train which is fitted with the metal drums. Okay, I am talking about the wheel which is fitted with an axle and with the metal drums. These drums rotate along with the axle. These drum will rotate. When the train is to be stopped, what we need to do is, a strong magnetic field has to be applied for these drum. Okay, when you apply the magnetic field for these drum using this very strong electromagnet, eddy currents is induced in the drum. These eddy current should oppose the change in the magnetic field, should oppose the motion of this axle, hence the train is brought to rest. This drum has brought to rest because the rotation of the drum is what causing the change in magnetic flux. Therefore, the eddy current which is produced in the drum should oppose the change in the magnetic field, should oppose the rotation of this drum. Therefore, the train is brought to rest because of the eddy current which is produced in the rotating drum when we apply a strong magnetic field to this drum. Okay, we have another application which is a speedometer. We have seen this speedometer in our automobiles, in our mopeds, in our cars. We have a speedometer. This speedometer will indicate the speed of the vehicle. Here, the tiny magnet rotates inside an aluminium drum. This tiny magnet will rotate inside an aluminium drum. The rotating magnet, this rotating magnet induces eddy current in the drum. We have a drum and a tiny rotating magnet. Because of the rotating magnet, it induces eddy current in the drum, which produces its own magnetic field. So, aluminium drum, eddy current is flowing. Because of the flow in the eddy current, it produces a magnetic field, and it is its own magnetic field. Now we have two fields here. One field is due to a tiny magnet, another field is due to the eddy current which is produced in the aluminium drum. This field interact with the field of the magnet. Okay, this field which is produced in the aluminium drum because of the rotation of the tiny magnet is interacting with the magnet and produce a torque in the drum. It produces a rotating force which is called torque. A torque is produced in the drum and this makes it to rotate. A pointer attached to the drum will get deflected and this pointer will indicate the speed of the vehicle. Now what actually happening is the torque which is produced because of the interaction of the fields. One field which is produced by the eddy current, another field is the tiny magnet field. Because of the interaction of the two fields, a torque is produced which makes it to rotate and a pointer attached to this will also get rotated and this get deflected and this pointer will indicate the speed of the vehicle. Yes. So we have understood what is eddy current is, how the eddy current is produced and what and all the applications of eddy current in our day-to-day life. We have studied some 5 different applications of eddy current and these are the expected questions for the exam. You can expect this application of eddy current for the exam. So these are some of the books which I referred. One is Griffiths of Introduction to Electrodynamics, and of course the two faculties of Tumkur University, and they have written exactly onto the syllabus the 2 books. You can also refer this, and we have another one, Brijlal and Subramaniam, Electrodynamics 7th edition. These are some of the good books. You go through it, you understand the concept of physics. Thank you.